So in this video, I'm going to present to you the proof of the chain rule in multivariable calculus. And I'll be using this theorem later on in order to prove the mean value theorem and some other key results in multivariable calculus. So let's just quickly go over the theorem itself. There are certain other definitions or preliminaries that we need to go over before we can write out the proof itself. So the theorem, you can break it out two parts. This is basically just setting everything up. So it says that S be a subset of R to the power of n, T be a subset of R to the power of m. Both of these are open sets. G is a function that maps from S to R to the power of m, and F is a function that maps from T to R to the power of L. We assume that or we take an element A in the set S, and such that G of A is an element of the set T. We then say that we define a function phi, which is basically the composition of f and g. In other words, or more particularly, it's f evaluated at g of x. And we note that this is well defined near A. And the reason why it's well defined near A is because of the fact that S and T are both open, and A is an element of S, which implies that A is an element of the interior of S, because S is open. And that allows us to conclude that the ball centered at A with radius epsilon is a subset of S, which means that g of x for any x that lies in the ball centered at A with some radius epsilon is well defined, and that gets mapped. And since g of A gets mapped to T, we can assume that every element in that ball also gets mapped to T, and thus f for that ball is f at g of x is also well defined because g of x lies in T. I know that's a little bit complicated, but it sounds complicated, but once you start writing that out, you'll see that indeed f at g of x is indeed well defined near A under the assumptions that we've just made. Okay, anyhow, so now this is just setting the stage. The chain rule is, or this is the theorem itself, of course, it's just setting the stage for the chain rule or the theorem itself. And now what we know is, or what this theorem states is then that if g is differentiable at A and f is differentiable at g of A, then phi is differentiable at A, and in particular the derivative of f composed with g of A is equal to the derivative of f evaluated at g of A times the derivative of g evaluated at A. So a few things that I would like to emphasize before we move on is the definition of differentiability. We are not going to use the traditional definition, or not, I wouldn't really call that a traditional definition, but the definition that you typically learn in high school. That is not the definition we'll be using. We'll be using an equivalent definition. So first of all, let me emphasize that the definition that you study in high school is limit as if that f is differentiable at a particular point, if limit as h approaches 0 of, let's say, f of a plus h minus f of a divided by h exists, and let's say it's equal to a particular number. In this case, let's say it's equal to m. Now let me just show you an equivalent definition. What you can do now is you can bring this m on this side. So what you get is limit as h approaches 0 of f of a plus h minus f of a divided by h, and I'm actually going to bring that m inside the limit. So I'm just going to write it as mh divided by h. Does not make a difference because the h's just cancel out. And this is equal to 0, and this allows me to write it something like this, minus mh divided by h. So now an equivalent definition would be that a function f is differentiable if and only if there exists a real number m such that limit as h approaches 0 of f of a plus h minus f of a minus mh divided by h is equal to 0. But this is only true for, of course, real valued functions whose domain and whose range are both a set of real numbers. Now, in this case, however, we don't want that. We want it to be, the chain rule in this case is a lot more general. It allows the domain and the range of f and g in this case to be r to the power of anything. So it could be r cubed, r2, basically anything. So what we do in that case is this definition can be generalized, and the way we generalize this to in multivariable calculus is we replace h with the vector h. So we say that a function is differentiable if and only if limit as vector h approaches the 0 vector of f evaluated at vector A plus vector H minus F at vector A minus capital M, where capital M is a matrix, times the vector H divided by norm of the vector H. This is equal to the 0 vector. If this is true, if this limit, if such a matrix M exists that satisfies this particular limit or this particular condition, we say that M is the derivative, then M is the derivative of f at A. Now, one key thing to notice is that when this is the case, we say that M is equal to df at A. So that is where this notation is coming from, this capital D. Okay. If you, this is still not the definition that we'll be using. I mean, we can further amend this definition to suit our needs. And the way we amend this definition is we notice that the numerator, this numerator in this limit, is a function of age. So it's entirely dependent on age. So if we can assume that f is differentiable, which means that this limit is indeed equal to 0, what we can say is that, let's say that this numerator over here, this numerator is equal to e at h. And we just write e of h over here. So now we know that a function is differentiable if and only if f at f evaluated at vector A plus vector H minus f evaluated at vector A minus a matrix M times the vector H is equal to E of H. This is the vector H, where E of vector H divided by the norm of vector H goes to 0 as the vector H tends to the 0 vector. So this is the definition that we'll be using. Notice this numerator can actually be solved for f at A plus H, and that is what I'm going to do, because this actually gives us a very intuitive idea about what the derivative really is. Because now if you think about it, we studied all through high school that a derivative essentially approximates a tangent line, or it is used to linearize a function near a particular point. And I mean, this is basically the idea behind all of that. Because if you think about it, what this is saying is that f at A plus H is approximately equal to a linear function. You can approximate what f of A plus H, f of A plus H is using a linear function that is f of A plus m times the vector H, assuming that H is very small, because we know that E of H, E evaluated at vector H divided by the norm of vector H goes to 0, goes to the 0 vector anyways. So for sufficiently small H, f evaluated at vector A plus vector H is approximately equal to f evaluated at vector A plus the derivative of f at A times the vector H. So this is the definition of the derivative that we'll be using. So one is a function differentiable. For our purposes, a function is differentiable if and only if there exists a matrix M such that f of A plus H is equal to f of A plus the matrix M times the vector H plus E of H, where E of H divided by the norm of H goes to the 0 vector as the vector H, as vector H approaches the 0 vector. That is the definition of differentiability that we'll be using in order to write out the proof of the chain rule. So let's begin. That is basically the only thing we need to know in order to write this proof out. So we've assumed everything. We're going to assume that G is differentiable at A. We're going to assume that F is differentiable at A and everything. So I'm just going to begin the proof after everything has been set up. So what a proof? It goes as follows. Firstly, as G is differentiable at A, as G is differentiable at A, we know that G at A plus H is equal to G at A plus the derivative of G at A. So let's just say dG at A times the vector H plus this is also sometimes called as the error in the approximation, so which is why it's denoted with a capital E. So it's E at H. Now, one thing that you'll see, or one thing that will become quite apparent is this fact that once you start writing out the proofs, you will get a lot of different, these error terms, and you need to keep track of them. So the way we are going to keep track of them is that we are going to label them. So this is the error term when we are approximating G at A. So this is the error term that we get when we approximate G at A of H. Similarly, as f is differentiable, at g of a, and I'm going to label g of a to be, let's say, equal to b, we know that f at a plus h, sorry, yep, okay, f at g of a plus h is equal to f evaluated, okay, hold on, let me just see this real quick. Yeah, so first of all, I guess before, no, in fact, you know what, we can just go ahead and write it out like this. So f at g of a plus the derivative of f evaluated at g of a times the vector h plus e, the error term, when we evaluate f at vector b of h. So we know that both of these things are true, but now we have to do a little bit of manipulation over here. This is how it's going to go. Then f evaluated, so now what I'm going to do is I'm going to see what phi at a plus h is. Phi at vector a plus h is equal to f evaluated at g of a plus h, and these are all vectors. I'm just not going to call them vector a plus vector a, just a plus h, but these are all vectors. Okay, so this now is equal to, so this is where you have to be a little bit careful. Now what I'm going to do is, because you need to keep track of all the terms, so this is g of a plus h, and I know that g of a plus h by our assumption or by our definition is equal to this piece right here, this one. So what I'm just going to do is I'm going to replace that with that. So I'm going to say f of g of a, this is equal to f of g of a plus the derivative of g of a evaluated with vector h, multiplied by vector h, plus the error term of g when we're evaluating it at a and evaluated at vector h. And now the idea is that if you look at this piece right here, these two are quite similar to each other, these two expressions, except for the fact that in this expression right here, we have the vector h, whereas over here we have a function of h. However, what we're going to do is we are going to call this w. We're going to call all of this w. So let's say that this is w. So this now is essentially equal to f evaluated at g of a plus the vector w. And now if you now look at it, we can basically expand f at g of a plus w using this expression. The only thing that we need to do is we need to replace h with w. So this, when we expand it out, will become f evaluated at g of a plus the derivative of f evaluated at g of a. So now I'm going to times it by the vector w, because we replaced the vector h with the vector w, plus the error term. So the error term will still be the error term of f and b evaluated at w. So the only thing that we've done is we replaced the vector h with the vector w, but now you'll see something really interesting. Phi of a plus h, vector a plus vector h is equal to this. So the interesting piece over here is that we are almost done. The only thing we need to do now is expand this w and then show that the error term does indeed go to 0. So let's expand this w, right? So we know what w is by definition. So plus the derivative of f evaluated at g of a, and then we know that the vector w is equal to the derivative of g of a times the vector h plus an error term g comma the vector a evaluated at h, and then we have this error term of f, and this one is evaluated at w. If you keep on expanding this, you're gonna get f evaluated at g of a plus df of g of a evaluated at g of a plus the derivative, times the derivative of g evaluated at a times the vector h, and then I'm going to write out this term plus e3, or just e of h comma w. Okay, I'm going to write it as a of h comma w because it's a function of both h and w, although I'm not sure if I should write it like that. But anyhow, so the underlying idea over here is that what we need to show is that this error term e of h comma w goes to 0. Now, if I'm able to show that, which I'll explain what that is in a minute, if I'm able to show that, notice that we are done. This is f of g of a. This is basically phi evaluated at a. This is what we want to show is the derivative. Now, remember, because this was what we wanted to show. The derivative of phi, or which is f composed with g evaluated at a, is precisely the derivative of f evaluated at g of a times the derivative of g at a, which is the same expression that we have right here. And then we have the error term, but we still need to show that this error term goes to 0. So where e of h comma w is equal to the derivative of f evaluated at g of a times the error term when we're one of the error terms when we're evaluating g at a plus the error term when f is being evaluated at, or being approximated at b, should say. And this basically this is just coming from multiplying these two together and this error term right here. So now what we need to show is that both of these terms go to 0. It's very easy to show that, the limit as vector h approaches the 0 vector of e of h comma w divided by the norm of h goes to 0. And it's very easy to show that for one of these terms, the other one actually requires some work. This one is easier to show, so let's just begin with it. So notice limit as h approaches the 0 vector of tf of g of a times the error term of vector h divided by the norm of h. This is equal to, I'm just going to bring this outside because this is just a constant, it's not dependent on h, evaluated at g of a times limit as h approaches 0, vector h approaches the 0 vector, e g of a of vector h divided by the norm of h. And this is where you have to take notice of the fact that g is differentiable. So by definition, this error term, this thing goes to 0. So this goes to the 0 vector as g is differentiable at a. And this basically is equal to the 0 vector. So we know that this thing goes to 0 as h goes to 0. Now we need to see what happened. We don't know that this thing goes to 0. We know that this expression divided by the norm of h goes to 0 as the vector h as vector goes to the 0 vector as vector h approaches the 0 vector. And we need to make the same conclusion about the second factor, although this one will be a little bit harder to do. So also now you have to be a little bit careful over here. Now this error term, this second error term, can actually be rewritten. So if I write this out as divided by w, by the norm of the norm of h. This is what we need to show goes to 0. However, notice that this is the same thing as the norm of w divided by the norm of h times this error term again divided by the norm of w, where we assume that the norm of w is not 0. Okay. So now this is basically where probably the hardest part of the proof. What we need to do are two things. The first thing is that we need to ensure that because remember, we're looking at what happens at vector a as vector h approaches the 0 vector. What we know is that this piece will go to 0 as w approaches the 0 vector, not as h approaches the 0 vector. What we need to show is that as h approaches the 0 vector, this entire expression goes to the 0 vector. However, what we also know is that this error term evaluated, which is being evaluated at vector w, divided by the norm of vector w, will go to 0 as w approaches the 0 vector. Now, why is that the case? This is simply because f is differentiable at b. So if f is differentiable at b, what we knew already was this, that if f is differentiable at b, then this thing goes to 0. The error term divided by the norm of h goes to 0 as vector h approaches the 0 vector. So if we want to do a change of variables, if we want to replace vector h with vector w in this entire expression, there are two things that we need to make sure, or in fact only one thing that we need to make sure, which is that as h approaches the 0 vector, w also approaches the 0 vector, so that we're not messing up with the limit itself. And that is fairly easy to do. The second thing that we need to do is ensure that this vector w divided by vector h, this does not behave weirdly. I mean, this does not go to infinity, for example, because if it does go to infinity, then we get an indeterminate form under the limit, and that is just going to complicate a lot of stuff. So and it turns out that this is actually quite easy to do. So let's just do this real quick. If you go on and if we look at this piece, this is what we define vector w to be. So I'm just going to copy paste this back. So we know that vector w is equal to this piece. Now, if you think about it, let's see what happens as h approaches the 0 vector over here. If h approaches the 0 vector, we know that this entire thing is going to go to 0 because dg of a, the derivative of j evaluated at a, is basically just a constant. And we also know that this term must go to the 0 vector. Why is that the case? Because we know that g is differentiable at a, so this limit does indeed go to 0. This limit divided by the norm of h, this one does indeed go to the 0 vector. However, if this numerator, if this independently does not go to 0, then there is no way that this entire limit can go to the 0 vector. Because what this limit is essentially saying is that the numerator goes to the 0 vector faster than the denominator. In other words, as h approaches the 0 vector, the numerator independently must also go to the 0 vector. So just intuitively, we know that it is indeed the case that as h approaches the 0 vector, as h approaches the 0 vector, w also approaches the 0 vector. That is basically the intuitive idea, but we can actually do something better. Now, what this implies is that the norm of w is equal to the norm of this entire piece, as e g comma a of vector h, and by the triangular inequality, this is less than equal to dg of a times the norm of h and plus e of g comma a evaluated at vector h. And this entire piece itself is less than or equal to just dg of a evaluated at vector h, because remember this is something that is always positive because it's a norm, so it will always be something positive. And dg of a is just a constant. I'm just going to label this constant capital K. So this is equal to capital K times the norm of h. And this implies that the norm of vector w is less than or equal to k times the norm of vector h, which implies that as limit as vector h approaches 0 of vector w is of the norm of vector w is indeed equal to the 0 vector. Because if h approaches the 0 vector, this entire thing goes to 0, which by the squeeze theorem implies that the norm of vector w also goes to 0, not the 0 vector because it's a norm, but this itself implies that limit as vector h approaches the 0 vector of the vector w is equal to the 0 vector. So this is in fact all the information we need. We can actually now go ahead and show that this error term goes to 0. Then limit as vector h approaches the 0 vector of this thing right here. This is equal to limit as h approaches the 0 vector of the norm of w divided by vector h times this error term divided by the norm of w. This itself now is equal to limit still as vector h approaches the 0 vector. What I'm going to do is I'm going to replace, this is actually less than or equal to. What I'm going to do is, in fact, one other mistake that I made, I'm going to consider this an absolute value, all of this an absolute, not an absolute value at the norm of this entire thing. Because if I can show that the norm goes to 0, then I know that the vector itself goes to the 0 vector. So for now, I'm just going to consider the norm. So this entire thing now is less than or equal to k times. So what I'm going to do now is I'm going to replace w with k times the vector h. So capital K times vector h divided by vector h, because we just proved that the norm of w is less than or equal to k times the norm of h. And I still have this entire piece, the norm of this error term divided by the norm of w. And this will just cancel out. This now is equal to limit as vector w approaches the 0 vector, because remember, if h goes to the 0 vector, w is also going to the 0 vector. So, and we don't need to make any other replacements over here inside this limit because we've gotten rid of all the terms with an h in it. So now we have only the w terms left over, or the terms that are being evaluated at the vector w. And now we're going to basically change the limit. Instead of saying that h goes to the 0 vector, we're now going to say w goes to the 0 vector, which are the same thing in this case, because as h approaches the 0 vector, so does the vector w. And then I'm going to left with k times the norm of the error term. These are all vectors of evaluated at vector w divided by, divided by the norm of the vector w. K is just a constant, so that does not matter. If you just ignore k for a second, we know that this term goes to 0 as f is differentiable at. Now in this case, this just goes to 0, not the 0 vector. So we know that this goes to 0 because of the fact that f is differentiable at b. So we know that this entire thing just goes to 0, which implies that limit as vector h approaches the 0 vector of the error term. So now I'm just getting rid of the norm in the numerator, evaluated at w divided by the norm of vector h is indeed equal to the 0 vector. And we can write a conclusive statement. Thus, phi of a plus h is equal to this entire piece. Copy. So I'm just going to paste it over here, but I'm going to make one little adjustment. Sorry about that. So, and the adjustment I'm going to make is I'm actually going to get rid of this w over here, because we know that w itself is dependent upon h, so we don't need that w anymore. Where the limit as h approaches 0 of e evaluated as vector h divided by the norm of vector h is equal to the 0 vector. Thus, or hence, phi is differentiable at a, and in particular the derivative of phi evaluated at a is equal to the derivative of f evaluated at g of a times the derivative of g evaluated at a. And this completes the proof of the chain rule. Yep. So yeah, that's pretty much it. As I said, it's not really a complicated proof. It's just that it's very important that you keep track of all the error terms. Um, and also it's just it's more of an algebra kind of a thing. So I mean, if you're stuck somewhere, it's probably because you have some you're having some trouble with keeping up with all the terms, or you made some algebraic error. Because as long as you know some basics about how limits work, and you know the basic limit laws, and you're familiar with the definition of differentiation in multivariable calculus, the proof is fairly straightforward, except for maybe proving that this thing goes to 0, that the error term, when it's evaluated at the vector w divided by the norm of h, goes to 0. This one might be a little bit harder than the rest of the proof, and this is probably the only thing that makes the proof a little bit harder. But overall, I would say that the proof is fairly straightforward. But if you have any issues with the proof, if you do not understand a particular concept, do let me know in the comments down below, and I'll be happy to go over it again. So yep, that's pretty much it for this video. In the upcoming videos, I'll be presenting the proof of the mean value theorem in one dimension, and then or in single variable, and then in multivariable calculus. It's variant in multivariable calculus. We'll be proving some results using the mean value theorem, and then I'll eventually present the proof of the implicit and the inverse function theorem. So yep, I hope you enjoyed the video, and I'll see you in